Good morning, ladies and gentlemen. It's a pleasure to be here today and to inform you about some of the developments currently underway at Hengtong Marine Cable Systems. Just one slide to inform you a little bit about the company. This is our global footprint. Most of our manufacturing facilities are in China. Hengtong is a cable manufacturing company. We make power cable and optical cable products. We've also got factories in Indonesia, South Africa, Brazil, Spain and Portugal. So our footprint globally is expanding. To look at the developments in subsea optical cable designs and why we have arrived at where we are today. Then look briefly at some of the Hengtong marine products. Look at the future design trends that we're seeing being requested by our clients, and then some final remarks. So, evolution of subsea cable design. Where we got to today. So going back about 30 years to the mid-1980s, saw the last of the coaxial analog submarine system deployments and a new breed of transmission cable being introduced, the optical fiber cable. So cable manufacturers at that stage had to come up with some new methods of packaging the optical fiber cables. Standard telephones and cables, where I started my career, adopted a tight buffered package where the fibers were embedded in a hydril package. Had some advantages and some disadvantages. The limitations of that design were the limited numbers of fibers that could be placed in the package, and the difficulty extracting the fibers from that package required sophisticated heating treatment, high pressure air to blow the hydril away, and that often damaged the fiber coatings and fiber colorings. So that was a problem area and a very restricted method of packaging fibers and cables. Other companies like Alcatel Submarcom adopted a slotted core design. And again, that had limitations on fiber count and some optical properties during installation. Really, the development of the way fibers were packaged were driven by clients. Clients requested increased fiber counts. They wanted improved fiber attenuation. They wanted higher, better quality control on fibers and time savings on the way fibers are extracted from the cable during marine jointing. Marine jointing, very weather sensitive operation, has to be done as quickly as possible. So any operations and time savings that can be made offshore are extremely valid. And really all those requirements attributed to the development of the fiber in metal tube, the loose tube design for submarine cables that we see today. So since the first design iteration in the mid-1980s, we've seen a trend to reduce the diameter of lightweight cable and for the tensile strength of lightweight cables to be reduced. Today, most of the lightweight cables are in the 17 to 18 millimeter diameter range and with a tensile strength of between 65 to 80 kilonewtons. So here we can see a graph of the cable diameter versus the cable weight in air, and it's been reducing, and the circled data points are really where the products lie today. So the implication of this graph is that because the cable diameter and cable weights have decreased, we can load the cable vessels with more cable and therefore offer clients a more cost-effective marine solution. Similarly, the cable diameter in UTS has fallen to, again, where we are today. Again, benefits to the client, smaller cables, less material, more cost-effective designs. Really, subsea cables are tailored to meet the client's requirements. Fiber counts and fiber specifications vary for almost every manufacturing run in the factory. Depends if the client wants a repeatered cable, a powered cable with optical amplifier units along the cable, or an unrepeatered cable. The design life of the cable also influences the cable design. The level of mechanical and electrical protection required can vary greatly. In the photograph to the right-hand side, you see lightweight cables, lightweight protected, and then externally armored cables. And the cable engineering and the selection of the right cable to mitigate risks of damage to the cable is a very important part in the design of any submarine cable system. Attitude to risk and system design. Again, if you're investing in a cable system that goes from point A to point B and it's your only subsea asset and you've got no redundancy available, you want to make sure that the cable's of the most robust and highest quality to be installed. If you're investing in a ring system and the cable gets cut, you're not going to lose traffic, so perhaps you're a little bit, you can take on board more risk than the first option. Finally, if you're a real global player and you've got a whole meshed system of cables available, you don't really mind if a link goes down for 2 or 3 months because you've got inbuilt redundancy and you can afford to wait for a marine repair operation. So different levels of risk influence the cost and the design of cables that operators want to purchase. Again, the cable design depends on the environment. If you're laying cables in a very calm, shallow water, benign seabed, the protection level, the threats are less, the protection level is less. If it's a very hostile, active sea with rocky outcrops, lots of fishing, anchoring, again, you want to have the best marine solution. You want to have a heavy armor and you want to bury the cable as much as possible, or add additional protection to the cable on the seabed. Budget plays a major influence on what you actually purchase and deploy subsea. And your repair and maintenance strategy. If it's a short system, perhaps you don't have a maintenance strategy. You'll just relay the short link. But most systems have to be maintained and repaired and enter some form of marine repair agreement. Okay, what should a successful cable design offer? This is really going to state the obvious. It should offer the best possible protection for the optical fibers, have stable, well understood manufacturing processes, and the highest possible quality control. We've heard a lot over the last days about the cost of quality. If you get it wrong, it can cost a lot of money. If you get it wrong subsea, it costs even more. The design should maintain the fiber attenuation properties during the cabling operation, during the loading, during the laying, during the recovery. All the cable that's recovered on board to make repair joints has to be redeployed onto the seabed. So you want to have a very stable cable structure that the fibers are protected. And really, you want to have a cable structure that doesn't change. So when you recover it, it stays straight, it lies in conformity with the seabed and the deck. You don't want it to corkscrew or to cause a hazard on the seabed that could enable the cable to be snagged and dragged. And obviously, you want to minimize the environmental impact of the system. So subsea cable designs generally fall into two basic types of cable: cables with a vault design and cables without a vault. So cables with a vault are generally designed to be deployed in 6,000 to 800 meters water depth. So these are transatlantic, trans-Pacific type cables. They are used because of the cable system length. They're generally repeatered, so that means that there's a powering requirement. So power as well as optical signals are sent down the cable. But the cable structure can also be used for unrepeatered systems. The Volt type cable design structure is supplied by all the major suppliers. So these are some of the cable systems that I'm sure you're familiar with, the OLC4, the SL17 and the URC2 cable families. Cables without a Volt are generally designed for shallower water systems, maybe up to 3,000 meters. And they're URC1 and mini sub, so we'll explain a little bit about the construction of those cables in a second. So they're generally smaller diameter, they use less materials, and they're cheaper to produce. So here we can see the Hengtong family of repeatered volted cable structure. So we've got 5 cable types: lightweight, lightweight protected, single armor light, single armor, and double armor. The volt structure is the inner armor design, where we use 3 sizes of inner armor wires under the copper tape, which nest together and form a very stable, robust structure, a bit like a Roman arch. So it's very, very good at withstanding hydrostatic pressure, and it's very good at providing excellent impact and crush resistance to the cable. So lightweight cables deployed down to 8,000 meters water depth, where the seabed is soft, it's benign, there are the risks of damage to the cable are low, because mankind doesn't operate in those kind of water depths today. Major causes of cable damage are anchoring and fishing, generally in 200 meters water depth or less. So external armor is applied to the lightweight cable to give additional weight and abrasion resistance and impact and crush resistance to the lightweight cable structure. So armored cables can be deployed down to 2,000 meter water depths, and double armor, which is the heaviest cable type, can be deployed down to 600 meters water depth. Purchasers don't generally use double armor cable to 600 meters water depth because it's very expensive. And depending on the cable route, 600 meters, to achieve a 600 meter water depth, you have to, the route length from the landing point can be considerable. So double armor may be used down to 100 or 200 meters water depth, but it depends on the threat level, the attitude of risk to the purchaser, and the overall cable design. So just looking at the structure in detail, this is a lightweight cable. So the lightweight cable can accommodate between 2 and 16 optical fibers surrounded by a jelly. The 16 fiber limit is really due to the manufacturers of the optical amplifiers or the repeater housings, which have a maximum limit of 8 fiber pairs. The continuously welded stainless steel metal tube gives excellent crush performance. It's filled with a jelly which limits the axial water penetration if in the event that the cable's cut or damaged subsea. The jelly contains hydrogen getters and provides the first and second hydrogen barriers to prevent aging or deterioration of the optical fibers over the 25-year design life of the cable. The fibers are inserted into the tube with slack so that the fiber doesn't come under tension during normal cable handling tensions and when the cable is strained. The volt structure, as I mentioned earlier, uses 3 sizes of steel wire. These wires bridge each other and provide excellent crush and hydrostatic pressure resistance. They also form the main strength member for the lightweight cable deployment and for recovery. The wires are completely flooded with a water blocking compound. The copper tape is continuously welded and provides the third hydrogen barrier, maintains the wires in the volt structure in their design position, and it acts as the electrical conductor for providing the power to power the subsea amplifiers and housings. And finally, the polyethylene insulation provides the obviously the electrical power insulator and resistance to water penetration radially. Quick look at Hengtong Marine submarine cables. Hengtong Marine can manufacture their own optical preforms, and we also can buy in fibers to meet client requirements. Today, Hengtong has the capability of manufacturing 60 million kilometers of optical fiber every year. So unrepeated cables, just touching on them briefly, are standard design with a vault structure can accommodate 24 fibers, but there are tube designs for 48, 96 and 192 fibers available. However, the higher fiber counts don't have the vault structure present. All the cables come with 5 levels of protection, so lightweight, lightweight protected, single armor light, single armor and double armor. And those 5 levels of cable protection allow adequate route engineering, cable engineering and route engineering selections. Unrepeated systems are designed to have a 500 volt operating voltage applied if the client wishes. Normally the client would monitor unrepeated cables for any sign of insulation degradation or failure as an early warning sign of a potential cable repair. And the copper tape for our unrepeated designs are also used for cable tracking, for burial and fault finding. The cables can be repaired using universal quick joint technology or by Hengtong Marine repair joints. And the cable structure has a successful field proven performance. The Comoros system and the NASCOM system were installed last year by eMarine, and those systems are both operational today. Here we can see a cross-section through our unrepeated cable design. So the cables are all designed to allow the safe deployment and recovery for repair, and a 25-year design life. For repeated cables, the fiber counts are lower, up to 16. Again, we've got 5 levels, 5 types of cable for offering different cable protection. The operating voltage for our repeated cables are 15 kV for the powering of subsea amplifiers, and also for the injection of tone for cable tracking. All the cables are qualified by the universal joint for marine repairs, and the cable structure has successfully completed sea trials. The main difference between the repeated and the unrepeated design is the thickness of the copper tape and the thickness of the polyethylene insulation. The outside diameter of the lightweight cable is 18 millimeters, and the double armor cable shown here has an outside diameter of about 35 millimeters. Cable manufacturing processes. The first process is the insertion of the fibers into the metal tube, and currently the factory are able to achieve lengths of between 100 and 150 kilometers without any joints. The process is limited by the size of the take-up at the end of the line. The inner armor and the welded copper tube process, the longest length process to date for an unrepeated system, is 300 kilometers without the use of any cable joints. The third operation in the manufacture of submarine cable is the extrusion of the lightweight insulation. And the final operation is the onward processing of the cable for lightweight protected or outer armor wire designs. So, system integration. Having made the cable to the system supplier will have undertaken a cable route survey and have delivered to the factory either a route position list or a straight line diagram indicating the lengths of the various cable types required. So the cables manufactured are stored in the correct order within final tanks, and the cable ends are brought up to an integration area to allow for jointing or inline transitions during manufacture. the system assembly and testing, the jointing of the cables, and the integration of repeaters into a repeater system is all done in the integration area. And finally, the system is loaded out to the cable ship and freighter in one continuous length. So there are three main loadout options. We can deliver cables in pans, we can deliver cables on freighters to save on cable ship time, or we can load the whole system directly to a cable ship. Future design trends. Really, we've seen client requirements in two directions, two diverse directions. Some clients want cost reductions. They want smaller cables, they want less material, they want cables with less copper content, and they want substitution of other materials other than copper. So very similar themes that were discussed yesterday for the power cable. We're seeing very similar trends in the submarine cable optical fiber market. And one unusual one is perhaps for Pacific Island nations, for remote island communities. There's a demand for a very low-cost optical fiber cable, where the clients only want one fiber pair, the absolute minimum. They want the least fiber protection that they can get away with. They don't want to go through the cycle of route engineering and marine survey. They want to do an echo sounder run and deploy one fiber type, one cable type from A to B, and take the risk that the cable will not be damaged in the inshore sections. If it is, they're prepared to take that risk on board and do a marine repair operation. Other clients want technical enhancements, and enhancements generally mean cost increases. So they want cables with reduced conductor resistance, i.e. more copper or a copper substitute, and this is aimed at very long haul systems. They want cables with larger, heavier armor wire for greater seabed stability. Larger armor wires are more difficult to displace, so the cables are more difficult to damage through external aggression. And they offer more material for abrasion resistance. So in one trend, we see client requests to lower costs. So they want less materials, shorter processing time, simplified cable engineering, just one cable type. They want the minimum number of fibers. They want reduced survey requirements, and they just want to surface lay the cable. They perceive the threat level allows them to do that. Different clients, other clients want to increase the costs. They want higher technical requirements, more material. They want slower processing speed, shorter lay lengths on the armor wires to improve the crushing resistance. They want cables that can be buried deeper into the seabed and recovered safely, and they're prepared to pay for additional cable protection at cable crossings and pipeline crossings where they perceive the risk is greater for cable damage. Some final remarks. Subsea cables will always be designed to meet client requirements, particularly in the oil and gas sector. The cables are always tailored to meet the client's requirements regarding fiber type, cable structure, and the required protection. As I mentioned earlier, some island communities, to have a viable business case, they need a different business model. They need to have a cheap one cable type for deployment, which may underprotect the cable in certain areas, but they're willing to take that risk on board. We're seeing cables being laid in new geographical areas, more cables being laid in the Arctic, the north of Canada, the north of Russia. These areas are unique. They've got a very restricted access due to the winter conditions, the ice coverage. So again, clients are wanting the very best, robust, crush-resistant cables that they can afford, because because of the perceived threat to the cables in those areas. And also for longer cable routes that are now being considered, and when I say longer, it's 10,000 kilometers plus. Again, the clients are wanting lower conductor resistance, primarily to control the size of the onshore power feeding equipment. Thank you very much for your attention.
Thank you.